Let's look at getting the pH of salt solutions. The salts we're going to look at come from neutralization reactions, and I do have this in quotes. You'll see why it's in quotes in a little bit. In a neutralization reaction, what we are going to see is an acid and a base reacting with each other to produce water and a salt. And we've done these types of neutralization reactions before. We're using the Arrhenius definition for acids and bases, so it's kind of like an ion exchange partner swap, where one thing in the reactants is giving up an H plus and the other thing is giving up an OH minus to give us water as one of our results. So first example, if we took hydrochloric acid, reacted it with sodium hydroxide, strong acid, strong base, we would get sodium chloride and water. And if we used perfect amounts, then after the reaction, the only thing left would be the sodium chloride and water. And this solution has a pH of 7. So it has a neutral pH. We took an acid, pH less than 7, a base, pH greater than 7, mix them together, and our result is a pH of 7. So we did get a neutral result from this reaction. So we'll try another one. If we took acetic acid and reacted it with sodium hydroxide, our products would be sodium acetate and water. This solution has a pH of 9. So if we had perfect amounts of acetic acid and sodium hydroxide when they react, so the only thing in the solution is sodium acetate and water, we would get a pH of 9. Also, if we took solid sodium acetate and dissolved it in water, if we made the same concentration, we would get a pH of 9. So the salt, the properties of the salt are making this solution basic. Now it's still a neutralization reaction because we reacted an acid with a base, we got a salt and water. It just so happened that the salt that we got is a base. So one of the products that we made is capable of acting like a base in solution, and you have enough information to predict which pieces will do what and to calculate the pH of solutions like this. So let's kind of break this apart to see where everything came from. So the sodium acetate, we're just going to work with the sodium acetate. So when you get these problems, you just want to work with the thing that is affecting the pH of the solution, which there's no more acetic acid and there's no more sodium hydroxide. So sodium acetate, this is a soluble salt. Acetates are, and so are salts of sodium. So in solution, this exists as Na plus and acetate. Acetate is the conjugate base of a weak acid. Acetate in solution can react with water to produce acetic acid and OH minus. So it's this OH minus that's produced by the acetate in solution that makes this solution basic. Okay, so I have the ions categorized by what would make an acidic solution, what would make a neutral solution, and what would make a basic solution. What you would do if you were given a salt and asked to determine if it's acidic or basic and then potentially calculate the pH is split it up into its component ions, figure out what each ion does in solution, so whether it makes an acidic, basic, or neutral solution, and put them together to see what you get at the end. We're going to do some examples once we get through this list. So things that produce acidic solutions, anything that is the conjugate acid of a weak base. So we just saw the conjugate base of a weak acid being a base in solution. The conjugate acid of a weak base will be acidic in solution. We have a couple of kind of intermediates on those polyprotic acids. So HSO4 minus ends up making an acidic solution. H2PO4 minus makes an acidic solution. These I'll be less likely to ask you about because both of these things are also amphiprotic. There's a different equation that you can use to calculate the pH of these. The other way that you can get an acidic solution is a small, highly charged metal cation. Um, Again, I'm not going to ask you about examples for these, but I just want to not leave it off of the list. But what will happen, and as you'll learn about some of these things in lab as well, is that the something like aluminum 3 plus, the water molecules will stick to this aluminum metal cation when it's dissolved in solution, and the water can get so comfortable being attached to the metal, and the metal can kind of pull that water molecule in super close to the point where the water will kick out a proton. So this is how you get an acidic solution from these things. Now, right, the conjugate acid of a weak base, conjugate base of a weak acid, right? You can kind of tell that all of this is tied to the conjugate seesaw. And I've got like a seesaw explanation here, but there are mathematical explanations that will also help that I'm always happy to go through if you would like to see them. So what the conjugate seesaw connects is an acid and its conjugate base, or a base and its conjugate acid. And if one of them is strong or higher on the end of the seesaw, then the other side has to be the opposite. They have to balance each other out. So if you have a strong acid, its conjugate base is very, very weak to the point of not being acidic or basic at all. So hydrochloric acid is a strong acid. Its conjugate base is chloride. Chloride is so bad at being a base that the pH of its solution is 7. It's not basic in any way. Now, where you end up for a weak acid or a weak base is that the one side, it's kind of in the middle. So, right, with how a seesaw works, because it's all balanced around a specific point, in this case, for us, it's all balanced around the kW of water. Um, if the base is in the middle, then its conjugate acid is also in the middle. So the conjugate acid of a weak base would produce an acidic solution. Okay, so conjugate seesaw in mind, we mentioned a couple of things. So neutral conjugate acid of a strong base. So any of the Na plus, Li plus, K plus, and then conjugate bases of strong acids. We just mentioned chloride. So now if you know your 6 or 7 strong acids, the counter ions for those, chloride, nitrate, would be neutral solutions. Things that produce basic solutions are the conjugate bases of weak acids, and don't forget to check the conjugate seesaw. So let's do some comparisons. So if you have a cation that would produce a neutral solution and an anion that would produce a basic solution, the solution will be basic. So you would have the cation not contributing at all, and the anion making the solution basic. Overall, it would be basic. An example of this is sodium fluoride. So sodium as a cation, that's the conjugate acid of a strong base, produces a neutral solution. Fluoride is the conjugate base of hydrofluoric acid. So this is the conjugate base of a weak acid. It would be a basic solution. If your cation would produce an acidic solution and the anion would be neutral, overall you would have an acidic solution. So ammonium chloride is a good example here. Ammonium is the conjugate acid of ammonia, so it would produce an acidic solution because ammonia is a weak base, and chloride is the conjugate base of a strong acid. If the cation is neutral and the anion is neutral, the solution is neutral. So magnesium chloride, sodium chloride, potassium nitrate, right? Conjugate acid of a strong base, conjugate base of a strong acid. If your cation is acidic and your anion is basic, then what do? You you can't predict unless you have data that tells you about the different parts of this salt solution. And we do have that data. So the example we're going to look at is ammonium fluoride. So we have the conjugate acid of a weak base, the conjugate base of a weak acid. Whether or not the solution is acidic or basic depends on which is stronger. So is the acid stronger, then you would have an acidic solution. Is the base stronger, then you would have a basic solution. Now, you may not know off the top of your head how you could compare something like this, but acid strength, base strength, use an equilibrium constant. So if we use Ka for ammonium, right, it's acting as an acid. I want the constant that tells me about how it acts as an acid. And the Kb for fluoride, which is acting as a base, so I want the constant that tells me about it acting like a base. I can compare those two values. Whichever one is stronger, meaning it has a bigger equilibrium constant, will control the pH of the solution. Ammonium fluoride dissolves in solution, right? We could look up all of the ammonium salts are soluble. We have our acid, we have our base. We know what we need a Ka and Kb for, but ammonium and fluoride do not appear in any of the Ka and Kb tables. What we do see is ammonia and hydrofluoric acid, so we have to use the fact that Ka and Kb are related through Kw to get the appropriate constant to compare. So Ka times Kb equals Kw for a conjugate pair. So this means the Ka for ammonium times the Kb for ammonia is 1 times 10 to the minus 14th. So the Kb for ammonia I can look up, and then I can calculate the Ka for ammonium. Same for fluoride. I can look up the Ka for hydrofluoric acid and calculate the Kb. So you should take some time to practice this calculation. Make sure you get the same numbers that I did. When you do it, you should get that ammonium has a Ka of 5.68 times 10 to the minus 10th, and fluoride has a Kb of 2.9 times 10 to the minus 11th. 10 to the minus 10 is bigger than 10 to the minus 11, so the Ka is stronger than the Kb. This solution will be acidic. So the explanation is that ammonium is stronger at being an acid than fluoride is at being a base. So the solution is acidic. Okay, so if only one part of the salt contributes, then that is the pH of the solution. If both parts of the salt could contribute to the pH, you have to compare their acid and base constants to see which is stronger. Now, for things that have an acid cation and an acidic cation and a basic anion, I will not ask you to calculate the pH of that solution. I will ask you to tell me if the solution is acidic or basic. So you should be able to do that, but you don't then need to calculate the pH of the solution. If there's only one active ion, you're perfectly capable. Well, you're perfectly capable of doing the other one, but we'll stick with the major one that will be the most important. So let's look at how this would be done. So we're going to calculate the pH of 0.15 molar calcium acetate. In solution, calcium acetate splits up into calcium 2 plus and 2 acetates. Calcium 2 plus is the conjugate acid of a strong base, so it would produce a neutral solution. And acetate is the conjugate base of a weak acid, so it would produce a basic solution. So this is the first thing. I have the salt that I want to calculate the pH of. I split it up. I mean, it has to be soluble. It has to go into solution, even just a little bit. So I split this up to look at the ions, figure out what I'm expecting, what's contributing, and then I move on using only the thing that affects the pH. So the reaction, this is right, it's a weak base. It's going to go in a rice table. The reaction that I'm looking for is just how does acetate affect the pH of the solution? It does so because acetate reacts with water, produces acetic acid and OH minus. This table will let me calculate the OH minus at equilibrium, which is what will tell me my pH. So I am doing a weak base problem. I just have to make sure that my reaction is correct and that all of my initial conditions are correct. So, right, this is one acetate reacting with water to produce acetic acid and OH minus. You have to leave it as one acetate doing this reaction because we're going to set all of this equal to the equilibrium constant, Kb. Kb is defined for 1 mole of something reacting. We have to use the reaction that matches the equilibrium constant because remember, if you change the reaction, you change the value of the equilibrium constant. Okay, so if it's just one acetate in this reaction, then the concentration, I just want the acetate concentration in solution, it is 0.3 because the concentration of calcium acetate was 0.15, and for every 1 mole of calcium acetate, you get 2 moles of acetate. So my acetate concentration initially is 0.3, 0 of the products, cross out my column for water, and then finish solving this like every other weak base problem I've done. So, and every equilibrium problem. I don't have any products. My reaction has to move to the right. Using stoichiometry, that would be minus x, and plus x in the change row. I have everything I need to fill in the equilibrium row. And products over reactants is equal to Kb. The Kb of acetate is Kw divided by the Ka of acetic acid. So I am looking at x squared over 0.3 minus x equals 5.6 times 10 to the minus 10th. This is amazingly far apart. We can assume that x is small. So x squared over 0.3 equals 5.6 times 10 to the minus 10. X is 1.296 times 10 to the minus 5th. And when I test this, I get less than 0.005%. So, right, 4.3 times 10 to the minus 3rd percent. Great assumption. I don't have to go back and do anything else. This X value is the OH minus concentration. So, right, I have to choose a path to go down. I'm going to do the POH and then solve for the pH. So the POH would be 4.89, which makes the pH 9.11. So this is definitely a basic solution, which is what I was expecting from my analysis of the salt pieces.